Hello and welcome. Most of us are familiar with the traditional way that a byte represents a value, where each bit is a power of 2. But did you know there's another way to represent numbers? Today we do a deep dive into binary coded decimal. We'll talk about what it is, what support the 6809 has for it, why you would ever use it, and how it measures up. Let's go! Check out my byte. My byte's got 8 bits. You can separate that into 2 pieces. The upper 4 bits you can call a nibble, and the lower 4 bits you can call a nibble. There's 2 nibbles to a byte.
Nibbles and bits, nibbles and bits. I'm gonna get me some nibbles and bits, nibbles and bits.
With binary coded decimal, you treat each nibble as a decimal digit. So for example, this lower nibble can take on values from 0 through 9, but once it gets beyond 9, it's no longer a valid binary coded decimal. So as we start cycling through the numbers, you can see that the binary coded decimal keeps on going up. But what happens when these bits go up to an A? It is no longer a valid binary coded decimal. So as we go A, B, C, D, E, F, that's not valid. But as soon as we go to the next number, now that lower nibble is back to 0, which is valid, and the upper nibble has now gone up to 1. That makes the binary coded decimal interpretation of this byte a 10. And once again, the lower nibble gives us the lower decimal digit. We ignore everything from A through F. And then the upper nibble gets to go up by 1, and we're at 20. And what happens when we keep on going up? Our low nibble gets into these invalid ranges and then comes back. What if we get all the way up to 99? What happens after this? Well, again, the lower nibble gets invalid, but then as soon as it flips over, it's valid again, but now the upper nibble is invalid because the upper nibble is A. So now we're in this range where the upper nibble stays invalid until we finally cycle back around to 0. So sometimes we're in these ranges where both nibbles are invalid, sometimes we're in the ranges where only one nibble is invalid, but make no mistake, if any nibble is invalid, that entire byte is not a valid binary coded decimal. It's not like it's a half valid binary coded decimal. You should not be using that byte as a binary coded decimal. And since we waste so many perfectly good values of bytes when we're using binary coded decimal, that tells us that binary coded decimal is in a way rather wasteful. If you're trying to encode numbers with the smallest possible amount of space, binary coded decimal is not the way to go. What support does the 6809 have for binary coded decimal? It's got one and only one instruction, and this is one of the most restrictive instructions there is. Exactly one addressing mode, exactly one register that it affects. And here's how you use it. You ensure that your A register is already a binary coded decimal, and then you add to that another byte that you ensure is already a binary coded decimal. You can do the add either with or without carry. And then you run the DAA, which decimal adjusts after addition the A register. For example, Hex 64 is a valid binary coded decimal, and a super easy way you can tell is if you look at the hex representation of a number and you're only seeing numerals in each of the hex digits, that is a valid binary coded decimal that is specifically decimal 64. And then in this example, we add to A another binary coded decimal number, hex 27, which again would represent the number where you interpret these as decimal digits. So we're really adding decimal 27 to A. After we do this, the A register will not be a valid binary coded decimal. So here we have a binary coded decimal of 64, and we're going to add to that a binary coded decimal of 27. When we do the addition instruction, we do not get a valid binary coded decimal because it's just doing straight, normal, regular addition. But if you do that addition followed by this magical DAA instruction, the DAA will take the value in A and just tweak it ever so slightly to give you the proper sum. So now we end up with 91, which is the decimal sum of 64 and 27. So again, the sequence is you ensure that the A register has a binary coded decimal. You use one of the addition operations to add to that something else that you ensure is already a valid binary coded decimal. And then you can use the 6809 to ensure that the sum is a valid binary coded decimal. So the DAA instruction only works with addition. It only works with the A register. It's very limiting. Well, you may be thinking, subtraction is just addition with negative numbers. Can we do negative binary coded decimals and then add the negatives of those to get a subtraction to work? Sort of. If you think about it the right way, you can get it to work in a very limited sense. With 2's complement, the inverse of a number can be found with 256 minus the original number. And for more details, check out this video on 2's complement. You can find a link to this video in the description. With binary coded decimal, the inverse of a number can be found by taking 100 minus that number. So as an example, let's look at what happens when we add binary coded decimal 64 and 80. After the DAA, we end up with 44. Which is what you would get when you throw away the uppermost digit. But it's also what you would get when you take 64 minus 20. And I got negative 20 by finding the inverse of 80 by taking 100 minus it. And as I continue to increase this number, I end up decreasing the magnitude of its inverse. So now the inverse we're looking at would be negative 16. And sure enough, 64 minus 16 is 48. I don't know if anyone actually does this, but I suppose it's possible. But what is the point of binary coded decimal? Why would anyone use binary coded decimal? If binary coded decimal just wastes perfectly good values, what's the benefit? Well, let's say, I don't know, you're writing a game and you want to display a score to the player. In fact, what if you're just writing any program and you want to display a number to the user for any reason at all? How would you even go about taking a byte or a series of bytes and then showing digits onto the screen, whether it's a graphic screen or a text screen? Keep in mind we have addition, subtraction, and multiplication, as well as an assortment of some other bit manipulation operations, but we don't have division. Here's some example code that might display a number onto the screen, and it would use division in a kind of do-it-yourself manner. If we had a number we wanted to display and that was in the D register, we could divide D by 1,000, and that would give us the thousands place. And then we would take the remainder and divide that by 100, and that would give us the hundreds place. And then we would take the remainder of that, divide that by 10, that would give us the tens place, and then finally the remainder of all that would just be the ones place. Since we don't have division, we have to kind of do that ourselves. This routine uses a loop of subtraction to figure out the quotient and the remainder. It starts with the dividend, and it continually subtracts the divisor, subtracts the divisor, subtracts the divisor. The number of times you need to do that until you end up with a result that's smaller than the divisor is your quotient, and whatever you're left with is your remainder. But just counting the number of times you're in the loop will just give you another number. What we need is something to print or something to draw. So in this case, rather than just counting the number of times we're in a loop, we continue to advance x into a table of numerals. This table of numerals contains the bytes that you need to poke into the high-resolution screen to get a particular numeral. Each entry has 7 bytes, so these 7 bytes tell you how to draw a 0, these 7 bytes tell you how to draw a 1, all the way up to 9. So we just advance x through that table 7 bytes at a time, each time through this loop. And then when this loop is done, x is now pointing at the bytes to put onto the screen. If you were printing onto the text screen, it would be a bit simpler because there's only 1 byte per numeral, and you could simply advance your pointer into that numeral table of VDG bytes 1 byte at a time. But this seems like a lot of work. We've got to do that whole subtraction loop for 1,000, then again for 100, then again for 10. In order to extract each digit from our number, we've got to do that loop a bunch of times. Now, how would this code look if we used binary coded decimal instead? Let's say once again that the value of the number that we want to draw onto the screen is sitting in the D register. We've got 2 bytes, and each of those bytes has 2 nibbles. So we start with the high nibble of the high byte. We mask the rest out, and we shift that high nibble to the right, and then we can use this. Right nibble BCD is some reusable code that takes the low nibble of the A register and uses that same numeral table to figure out what bytes to display on the high-resolution graphics screen. So we can assume only the low nibble is set, and so A itself is just going to be a value from 0 to 9. That's the binary coded decimal digit for that low nibble. And we can do a straightforward multiplication. If A is the numeral we're printing, and B is the number of bytes that the numeral table has for each entry, then A times B gives us the index we want into that numeral table. In fact, we know that A times B is going to be fairly small, 8 bits. So we can just use this nifty instruction to add B to X to index in. And now that we're indexed in, we can use those bytes to draw to the screen. So we're just doing that process 4 times. High nibble high byte, low nibble high byte, high nibble low byte, low nibble low byte, and that's it. Now this code you're seeing is a test to compare the speeds of drawing numbers using the BCD approach versus using the straightforward byte and division approach. And the idea is we're going to have a counter that just goes up, 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 and we're going to use BCD to print it, and we're going to use the regular division approach to print it. As the counter goes up, we have some work to do on the BCD side to ensure that the byte stays within the BCD realm. And this admittedly takes much more bookkeeping than the other approach where I would just increment D. In the BCD world, I start with the low byte, I add 1, and then I decimal adjust that. I preserve that low byte onto the stack. I load the high byte from the stack into A, because remember, we can only use the A register, and even though we have 2 bytes that we want to be adding 1 to, I can only use A. So I do this weird thing. This may not be the most efficient way, but I'm taking the carry bit that was set the last time that I did my addition. So when I added 1 to the low byte, the carry bit was set. This then takes that carry bit and adds it to my high byte. Most of the time this will do nothing. Some of the time it will be adding 1. In any case, we then do the decimal adjust for that high byte, preserve that high byte back onto the stack, and then we can go back to the top of the loop so that we can print this new word on our stack to the high-resolution graphics screen. And to compare that with what we do when we're testing the performance of the regular division approach, we're just adding 1 to the D register. So admittedly, there's a lot more work going on in the BCD approach, at least for this part. Maintaining your bytes in the BCD format does take some work. So let's go ahead and run this. And I'm going to show side by side the progress that counter divide makes versus the progress that counter BCD makes. Let's see if one of them is faster than the other. So with that test, we could use our eyes, and it did seem like the BCD approach was much faster. We can do a bit of a trick with the MAME debugger to get more of a feel for how much faster it is. I can have the debugger stop at every vsync, and we can look at the screen and see how many digits we got through since the last vsync, and we can compare that interval between the BCD approach and the division approach. So I'm going to run this, and it's going to do the division approach first. And then I'm going to hit F7, and that will have the debugger stop at the next vsync. And then I'm just going to hit F7, 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 and then we're going to see what the delta is of the digits between each vsync. Okay, so we're showing 567. I'm going to hit F7. I think that might be a 576. 92, 08, 26, 43, 59, 75, 99, 05, 23, 39. You'll notice, by the way, that the delta is going to be influenced by what the number actually is, the numbers are that we're doing the division on, because those loops don't execute the same number of times every time. It's totally dependent on how big each of the digits are that we're subtracting those divisors from. So now we're going to set a breakpoint just before the BCD version starts. And we're going to do this trick again. We're going to hit F7 a couple times to get this primed and ready to go. All right, maybe we'll start here. So we've got 20, 46, 72, 98, 124, 57, 77, 03, 30, 56, 83, 09, 36, 62, 88, 15, 41. Looks like the deltas had some variance here as well, but for the most part they stayed pretty stable, and were certainly much higher than the division approach. Looks like we were able to draw a good 2/3 more numbers between each vsync than we could with division. But of course this test is very sensitive to the actual code that I actually wrote. I have a link to the code in the description if you would like to look at it for yourself. In particular, if you find any optimizations I should have done to make this a more fair test, please feel free to leave a comment. And one other kind of fun thing I'd like to point out. If I set a breakpoint right here, this is in the BCD approach after we've added 1. So at this point, the 2 bytes of our counter are on the stack. And if I then take a look at those 2 bytes on the stack, they're here and here. Each time I hit the breakpoint, as you would expect, they go up by 1, but keep in mind these are hex digits. And what happens after I get to 469? I get 470. So it's like, even though I'm looking at hex, I'm seeing decimal digits. And that's because each nibble, each hex digit, is only allowed to range from 0 to 9. And once it gets up to 9, it wraps around to 0, and then the next most significant digit has its turn to increment up. So I just think it's kind of funny. I don't know, it caught me by surprise a bit the first time I saw this, but in retrospect it's fairly straightforward why it would do it. Well, that wraps up our exploration into binary coded decimal and DA. In the description you'll find links to the test that I used, as well as the binary playground tool that I used for some of the visualization. Until next time, thank you for watching.